Hello and welcome to this video on how to do some analysis or interpretation of a full factorial single replicate experimental design. The goal in doing a full factorial single replicate design is to determine which of several factors are important in affecting a variable of interest and to come up with a model of how they affect that variable of interest. So here we have a regression model of the type that would be generated in this analysis. x1 is the variable that corresponds to a factor, and x1 can take values of -1 or 1. Similarly, x2 corresponds to another factor, 3 and 4, and so on. Doing the analysis gives us values for beta 1, beta 2, beta 3, beta 4, and also these interaction terms, beta 1, 2, beta 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. We don't have higher order interaction terms because we're assuming that the third order and fourth order interaction terms are negligible, and we use them to get an estimate of the random variation on our response variable, on our y. Doing the analysis of the experiment tells us which factors are significant, in the sense that it tells us which of these coefficients are significantly different than 0. A coefficient close to 0 means that the corresponding factor is not significant for the model. So for example, if we did an analysis and discovered that factors b and d and their interaction bd were significant, then in the model we could eliminate terms that do not include b or d. So this term, which corresponds to factor a typically, could be eliminated. This term, which corresponds to factor c, could be eliminated. And all of the interaction terms, except for the one that corresponds to BD, could be eliminated. So again, this is actually one of the fundamental reasons we do the experimental analysis, to determine which factors are significant and have to be considered in our model that relates the response variable we're looking at to the factors. Eliminating these factors gives the following linear model. Now, because in our model we've thrown away information, that is, we've thrown away the coefficients beta 1, beta 3, and all of the interaction coefficients except beta 2, 4, there may be a question of whether or not our model is still valid. We can check this by computing the model residuals. As you'll recall, a residual is a response value minus the value predicted by the model for given values of our factor variables. If I have 4 factors, that would correspond to 16 different combinations of factor variables, which would give me 16 different response values, and for which I could compute the predicted values, and I would look then at these residuals. So here I've opened up the data file that describes my experiment in terms of factor settings and the resulting response variable. In order to check my model, and in particular check the residuals, I do the following. First, I have to set up the experiment. I select my factors, indicate the low-high values, select my response, and now I go to the terms. At this point, I do something different than what I did to determine which of the factors and interactions are significant. I select only the factors that have been determined to be significant. So let's move all of the factors out, select B and D and BD. These are the factors and interactions that I have determined are significant. Then I hit OK. Then I select the graphs I want, and in this case I really want a normal plot of the residuals. And I hit OK. So if my model is good, my residuals should be normal and fall close to the straight blue line. These residuals are not as good as they could be, but there aren't any really large deviations from the straight line. At the risk of being more confusing than I already am, if you can imagine that's possible, I have now a comparison of the two sets of residuals. The residuals on the left are the ones we just computed. The residual plot on the right is the residuals using all of the terms in the regression model, that is, even the terms that are close to 0. And you can see that the residuals on the right are somewhat closer to the straight line than the residuals on the left. This is because a model with all of the terms, which include all of the factors, even though their coefficients are close to zero, is more accurate than the model that includes only the significant factors. On the other hand, the model that includes all of the factors is not very useful to us because it doesn't really tell us which factors dramatically affect the response variable. As an example of this, let's go back and look at our model. When our model has only two significant factors, I can easily plug in values for these factors and determine which set of values maximizes my response variable. In other words, I could plug in -1 for x2 and -1 for x4, plug it in here, and compute y hat. Then I can plug in 1 for x2, -1 for x4, the same down here, and compute y hat again. And I have 4 different combinations I need to check to determine which factor values give me the best response. So that concludes this video on how to do some interpretation of the regression model generated by a full factorial single replicate experiment. Thanks for watching.